Ladies and gentlemen, this is the video for day 2. It should be Wednesday, April 4th. And if you're watching this, I am probably at the state capitol fighting for you guys' education and fighting for us to have some money so that we can actually be in school and do awesome things. So, first of all, problem sets. This video will go with problem set number 2. So by the time this video is done, you'll be able to complete number 2. Set 1 goes with the last couple of videos. Hopefully you've already done that, or at least figured out when you're going to do that. The 5.1 sets should be done by now. I will be collecting those when we get back, so make sure those are done as well. But with this video, I'm going to start by doing something I promised I would do in the last couple of videos. I'm going to explain to you why our regression line is called the least squares regression line, why that's so important. I'm going to do it using my Fathom software. I'm also going to show you R squared, the R squared statistic. This is something I think I mentioned last year in pre-calc, but we didn't really get into what it means. The other thing is that R squared, the basics of it is that it is the R value squared. You know, it's calculating it's easy. It's what you think it would be. But it has a very particular meaning, and we're going to talk about why it's so important and so interesting. So let's start with this. We're going to start with the data that we talked about last video, and a data set that a number of you collected last time, the height versus right foot, right? This data set, this scatter plot hopefully looks familiar to you. But what I've done is I've put a line here, as you can see. And this line is right at about 9.52. It's actually 9.53, that's the closest I could get it. But 9.52 is the average of the right foot length, right? So if X was no predictor of Y, if there was no correlation, if this was useless to us, well then the best thing we would have is just the average of the right feet, right? I mean that's the best predictor we have if we just had this data. If the heights meant nothing, this is what we would use to predict what the average right foot length is, right? But as we can see, there does appear to be a relationship. So we're going to make a comparison of what it's like if there was no relationship versus if there is one. So what we use to do that is something called the sum of squares. And I'm going to show squares. Here it is. I'm going to show you squares. Look at my lovely squares. As you can see, these squares come from distance between my line and the actual data points. So, in a sense, it's your y values versus the y hat. So, in this line, our y hat is just 9.52, or 9.53 in this case. It's close enough. It really doesn't make a difference. The sum of squares is 10.68. So, the area of all these squares. So, the distance from 9.52 to each actual y value squared is 10.68. So let's take a look at that for a sec. Now here's the thing, you can see some of these squares are quite big, right? That's a clear indicator that this model does not really predict the data very well, does it? No, of course not, because we can see there's an upward trend, and this line doesn't describe that. So I'm going to try and move this line around a little bit, and you'll see once I do, these squares make a little smaller, don't they? My sum of squares is down to 6.8. We'll see if I can make it better. Let me see if I can line this up even a little better. I'm down to 2.716. See if I can still do better. Let me see. Oh, that square is a little big. See if I can do something about that. I'm down to 1.99. I'm less than 2 now. So you see, I was at like 10.68 originally. And now I've gotten to under 2, 1.981. See how my squares are much smaller? That indicates this line is a better and better fit for the data. So what I'm going to do now is I'm going to get rid of this movable little line. And I'm going to put in the least squares regression line. And this line, based on calculations by the computer, is the line that will give us the smallest sum of squares. And there it is, 1.968. Excuse me. So we got pretty close with that movable line, right? I was able to get it down to about 1.9 or so. 1.99 or about 1.98. But I was really close. The smallest sum of squares possible is 1.968. And that's from this line right here. It gives me a little equation. And this should look familiar because this is the equation that we did yesterday. It's 0.227x minus 5.125. Oops. No. What did I do? What have I done? Oh. Scared the crap out of myself is what I did. Okay, it's here. We're good. Let's see if we can drag this a little bit so it's not up against the wall here. There we go. Come on. Stop that, you. So it'd be y hat equals, and I'll put the 5 at the end there like I was supposed to. Whew, okay, that was almost a disaster. But it wasn't. We're good. So, again, you can see the accretion equation. It gives us the sum of squares, right? Now this sum of squares is 1.968. 1.968. Put that here. And that's real nice because originally my sum of squares, if we just look at the mean, if there was no relationship, it was 10.68. So we were really able to cut down a lot of this fluff, if you will, a lot of this extra room in those squares. Now you also notice with this readout, it gives r squared right here. R squared is 0.82. Let me show you where that comes from. So, I went from 10.68 to 1.968, right? That is a difference of, if I can get my calculator real quick. Let's see, 10.68 minus 1.968, that's 8.712. I was able to get my sum of squares to go down from here to here. I was able to make a decrease by 8.712. Now here's the thing, it's 8.712 out of what I originally started with, right? Out of that 10.68. So out of that 10.68, I was able to get rid of 8.712 by way of the least squares regression line. And so, as a percentage, 8.712 out of 10.68, that is, as a decimal, 0.8157. Of course, if you round it, it becomes 82. There it is, right here. That's what R squares is, folks. It's basically the percentage of the least squares that is eliminated by having this line. So it's basically the percentage of the variability in the y variable, which is our right foot length, that gets accounted for by this linear relationship. Because as a result of this linear relationship, as a result of this least squares regression line, we're able to account for 82% of the sum of squares. Now, of course, there's still squares, right? There's still some variability. The line's not perfect. So, that 18% is due to other factors. Maybe it's sampling error, maybe it's just, differences in people. Your height is not a perfect predictor of your right foot length, and I don't think anyone would claim that, but still a very good one. Your height accounts for 82% of your right foot length. And then the other 18% will be accounted for by other factors, according to this data. Now, of course, that's only 12 data points. We need more data to get a better idea of what the truth is. But based on our data set, 82% of your right foot length is a result of your height. Is what that's saying, basically. So, let's just look at this for another sec if you want to pause it. Again, this sum of squares, if you ever go into advanced statistics, which I think a number of you might when you get to college, I hope you do, the sum of squares really comes out big time. It's something that really is an influence and a factor in a lot of different statistics that you'll study. This is all you're really going to see of it here. AP exam doesn't really make you do much with it, but just know that it's important. Just understand that the smaller that the sum of squares is, the better, right? Because that indicates that we're close to the data points. The further away you are from the data point, the bigger the square is. You guys saw that when I had the straight line. We had a real big square down here, we had a big square up here, but now they're all nice and small. And that's what we want, make it as small as possible. So that's what it is, folks. That's the idea of the least squares regression line. It's the line that makes the squares the smallest. The sum of the squares cannot be smaller than what it is with the least squares regression line. I'm going to talk about r squared as well. So, let's talk about this. So first of all, we're going to find and interpret the slope. This should be a review of yesterday, but just to recap, we can predict that y, which is our right foot length, will increase, because it's a positive slope, right? Increase by 0.227 inches, right? For each additional inch of height. So the slope tells us one thing. The slope tells us what's the relationship on average. Based on the regression line, we can predict that 1 inch increase in height will lead to 0.227 inch increase in right foot length, and so on and so forth. R squared is a measure of the strength of that relationship, and so is R, but R squared more specifically is the percentage of the variability in y that's accounted for by that linear relationship in x. So that's 0.82, so about 82% of the variability and that's what those squares measure, right? The bigger the square is, the further away you are from the line. So that's a measure of variability. It's a measure of spread. So 82% of the variability of right foot lengths can be accounted for by its linear. It's important. Remember, R has to be linear, right? So does R squared. Relationship with height. Again, that's sum of squares. We were able to reduce it by 82% by making the least squares regression line, which means 82% of that variability can be basically eliminated or accounted for by its linear relationship with x. So this is how you would phrase it. Again, I'll cover this again in notes, but this is what r squared is. That's what it tells us. And then number 3, calculate the value of r. Well, if r squared is 0.82, should be obvious what we do here is take the square root. So square root of 0.82, well, let's find what that is. Let me see, square root, no, come on. Ugh. It's being a clown. Square root of 0.82, that's about 0.91, 0.9055, somewhere around that to 0.91. And that should make sense, right? There is a strong relationship. Now, we can see the relationship's positive, right? Because the slope's positive. So we'll keep this positive. However, you will have to be careful. Because r squared will not tell you if the slope's positive or negative. Because think about it this way, that percentage is always going to be positive. Just like anything squared is positive, right? For example, if I had r was, let's go with 0.9, right? 0.9 squared is 0.81. Now if r was negative 0.9, negative 0.9 squared, well, negative times negative, or negative squared, that's also positive. So I'm just showing you, for example, 0.9 and negative 0.9 will get the same r squared value, and it'll be positive both times. So you have to be able to figure out what sign should r have. This time it's positive because, again, it was a positive relationship. But be careful. Be very careful. There will be times when you have to account for a sign change. And we'll talk about that when we get to examples. But I'll move aside. I'll try to look at this. You can pause the video if you want. again, these, kind of like how with p-value, you just say, hey, fail to reject or reject, and we have significant evidence, blah, blah, blah. Or with confident intervals, I'm 95% confident that, and you just fill in the script. Slope and r squared are just like that. Just know the script. Just know what it means, know those definitions. Last year, they had to do this one on the AP exam. They had to do the slope one. And it wouldn't surprise me if the r squared one showed up as well. It has before. So those are definitions you just got to know. Again, we'll put them in notes. We'll do more examples of them. And you have problem sets to practice them. So you'll be pros. It's not that hard. You guys can handle it. But just letting you guys know what's coming up. So I think it's notes time, right? Yeah. So get your notes. If you want to pause the video while you fish out your notes, you can do that. If you already have your notes in front of you, well played. That's smart. So again, r squared, sometimes written like this, r squared abbreviated like that, is the percentage of the variability in y that can be accounted for by its linear relationship with x. So, like our earlier example, 82% of the variability in foot lengths was accounted for by its linear relationship with the height. That sum of squares went down 82% once we actually made a line that fit the data as opposed to just looking at the average foot length. It's also called the coefficient of determination. So this is another vocab term to know. Coefficient of determination is r squared. Correlation coefficient is r. So don't get confused between the two. R is the correlation coefficient. R squared is the coefficient of determination. Nothing to be careful of. R squared is a percentage, R is not. So when you're talking about R squared, or the coefficient of determination, make sure you're saying a percentage. Like in the earlier example, we said 82% of, so on and so forth. R is not a percentage though. Never make R a percentage. Do not do that. Do not try to do that. That's not what R is. R squared is a percentage, R is not a percentage. Then using r squared to find r, we talked a little bit about this. Obviously take the square root. But then you have to think, does r need to be positive or negative? Your calculator won't tell you. It'll give you a positive answer every time. You have to use your head to figure out, is r supposed to be positive or is r supposed to be negative? So that's your job. Calculator will not do that for you. It can't. It doesn't know. You have to figure out, do I need a positive or a negative r in this situation? Alright, so short notes today. 3 examples. Let's knock this out. Again, like I promised, this video is much shorter than the one yesterday. Because really all I'm doing is introducing r squared and building off of what we did yesterday with the regression lines and all that fun stuff. Okay, first problem. So we got a relationship between the child's age when they say their first word and their score on the Gestual Aptitude Test later in life has this least squared regression line. And again, I gave it to you in a format where the variables are written in. If you just use x and y, you have to define x and y, but they put the variables right in there, so they don't have to. So you got this aptitude test called the Gestual test. It's just one of many aptitude tests out there. But we're looking at the relationship between a child's first word and their score on that. And we see the r squared of 0.41. And what that means is 41% of the variability in Gestual scores, that's one S, oops, Gestual scores. Obviously, there's going to be variability in that, right? Not everyone scores the same on aptitude tests, just like not everyone has the same right foot length. There's variability. But 41% of that variability can be accounted for by its linear relationship with in this case is the age at which children say their first word. So if you just compared ages with the average Jessel score, you'd get a sum of squares, right? But then if you adjust the line so it accounts for the linear relationship, that sum of squares will go down by 41%. Just like in our earlier example, that sum of squares went down 82%. So you can see it doesn't go down as much this time, right? This is only 41% decrease. That should show you that this relationship's not as strong as the one we had. And in fact, you'll figure that out because we're about to find the R value, right? And we're going to do that by taking the square root of 0.41. So we know R squared is 0.41. That means R is the square root of 0.41. And we're going to find out what that is. Square root of 0.41. 0.64. Right about 0.64. It was around 0.64. Now, does it need to be positive or negative? Well, if we look in the equation, that's a negative slope. So slope is negative. So R is negative. So if you say 0.64, that's wrong. It's negative 0.64. That's your final answer, folks. That correlation coefficient is negative 0.64. So you can see this is a moderately strong relationship. So last time it was a really strong relationship because we had a high R value and we had a high R squared value. You'll notice smaller R squared values are going to indicate weaker relationships. So again, look at R value to determine strength. Like 0.41 R squared is still moderately strong because we look at R to determine strength, not R squared. But there is a relationship. The smaller R squared is, the smaller R is. And that should make sense, right? So R squared is, it's kind of a clue as to strength, almost. You know, if you have a high R squared value, that R value is going to be high. Kind of a medium R squared value, kind of gives you a middle of the road R value, get moderately strong. If you have a very small R squared, well, you're going to have a very small R. But again, use R to determine the strength. Do not use R squared for that. R squared is for the percent of variability accounted for by your linear relationship. And again, use the context to figure out the sign. Again, this is wrong, this is right. Second example. A study on the number of absences a student has per year and their GPA reveals a linear relationship with a correlation coefficient of negative 0.43. Correlation coefficient, is that R or is that R squared? That is R. And this part, coefficient of determination, well, I was nice enough to tell you it's R squared, but still, make sure you know that. First one, I'm asking for R. And that tells us that there is a weak, negative, and it tells us it's linear. Because remember, R assumes it's linear. R doesn't care if your data actually is linear. It makes the assumption that it's linear. So we'll talk about when it's not linear when we come back. That's the first thing we're going to talk about, when the data is curved. But for now, let's worry about it being linear. Because again, I tell you it's linear. Relationship between number of absences and GPA. Number two, we're going to calculate and interpret that R squared. So first we've got to calculate it, right? Well, if R equals negative 0.43, R squared is going to be negative 0.43 squared, and let's find out what that is. Again, make sure it's in parentheses, guys. Because if it's not, you might get a negative answer. Obviously, R squared always going to be positive. If you guys can see it, it's 0.1849. So that is 18.49% of the variability in y, and your y value in this case is GPA, right? Because your explanatory would be absences, because absences cause your GPA to go down. GPA does not cause absences. In fact, I'll mark that right here. Absences, that's your explanatory variable. GPA, that's your response variable. Variability in GPA can be accounted for by its linear relationship with number of absences per year. There it is. So 18.49% of the variability in GPA can be accounted for by its linear relationship with number of absences per year. Now you notice this isn't all that big of a percentage, right? Reason that is because, well, our R value is fairly weak, right? That's not a very strong relationship. It's a fairly weak relationship, which means not a whole lot of this variability is explained by an explanatory variable. 18% is a bit, right? That indicates that absences are probably a factor. Again, there is some correlation here, but most of it's going to be other factors. The fact that people's GPAs are so different, there's more to it than just absences. And that should make sense, right? You know, absences play a role, but there's lots of other things that influence GPA. You know, intelligence, work ethic. You know, just because someone's here, present, doesn't mean they're trying hard. You know, who they have the previous year, have they had good teachers in the past? That plays a role. You know, again, so many factors that play into it. So just this one variable, just the absences, only accounts for about 18.5% of that variability. So again, weaker relationship, smaller the R squared is going to be. Same here. This one was a little stronger, right? You know, the age at which you speak your first word, you know, it's a sign of how precocious you are, how intellectually advanced you are. And so you can see it leads to a stronger correlation and a higher R squared value, which was 41% in this case. So I just want you guys to see the relationship between R and R squared. Weaker relationships mean that the explanatory variable does not account for the response as much as a stronger relationship would. Again, there's some here. Again, don't ignore this. That's still a decent chunk, but it's not the majority by any means. There's still, you know, over 80% of that variability explained by other factors. And we'd have to do more research to see what those other factors are. Last one. So look what I have here for y'all, folks. It's another computer output. AP exam loves computer outputs. You've got to be familiar with these. So again, you have your coefficient. This is the column that you need to look at for now. This other stuff we'll worry about later. And you'll notice off to the side, here's R squared, right? You see, that's a pretty darn big R squared, so this is a very strong relationship. And that should make sense, right? Because we're talking about the relationship between the drop height, where you drop a toy soldier, and then how long it takes to hit the ground. And you would think how high up you are is a very big influence of how long it will take to hit the ground. And the only other factors I can think of is maybe air resistance or something like that, but again, the big one is how high up you are. The higher up you are, the longer it's going to take to hit the ground. That should make sense. So first we're going to write the equation of the regression line. We're going to find your variables either in the equation or separately. I'm going to do it in the equation because it's easier. So our explanatory variable is right here. Again, that's our x, because slope always goes with x, right? So slope, and that's with x. And then obviously constant is just another word for y-intercept, just like we talked about in the last video. So y is not drop height's x, and so what's it, the time hat equals Let me see, that's 0.0057244 drop height. Minus 0.03761. Again, if you want to put y hat and x, that's fine, but you would have to say y hat equals predicted time to hit the ground and x equals drop height. You would have to write that out and say that. So again, those are your options. Again, this is the quick one right here. Interpret the meaning of the r squared value. So r squared is 92.2%. Sometimes it's given to you as a percentage. That's nice. Sometimes it's not. If it's given to you as a decimal, make it into a percentage. But 92.2% of the variability in drop height can, no, I lied. Whoops. No, my y value is the time, right? In the time it takes for toy soldiers to hit the ground can be accounted for by its linear relationship with drop height. Yeah, folks, almost made a mistake there. Be careful. Make sure you know which variable is which. In fact, it might not hurt to write out your explanatory variable is drop height, and your response variable is the time to hit ground. So again, like when you're calculating slope or when you're analyzing r squared, you have to know which variable is which. In both of those instances, it's y first. So in slope, we predict that y will change by however much for one increase of x. For r squared, it's, this percent of the variability in y is accounted for by its relationship with x. Because, when we talk about, linear equations, it's always change of y over change of x, right? So it's y first, then x, in both these interpretations. So you have to know which one's which. Explanatory variable, which of course is x, and response variable, which is y. Not a bad idea to write those out. If it's hard to tell, or you get tripped up the way I almost did, be careful about that. Alright, last one. Kind of like we did before, calculate and interpret r. So we know r squared, we got to make it a decimal, right? 0.922. So that's the thing about it being a percentage. Made it easier in number 2, but now you have to use your head in number 3. So do not take the square root of 92.2. It's the square root of 0.922. And if we do that, let's see, 0.922, you get 0.9602. So I'm just going to round to 0.96. R equals 0.96. Let me see. Should be positive, right? Slope's positive. So r is positive. So there is a strong positive, we're assuming linear, right? We'll say assumed linear relationship between drop height and time it takes for toy soldiers to hit the ground. Okay, there it is, folks. That's r squared. Again, tied into what we talked about earlier, about r and about slopes and regression equations. So it's just an added dimension. It's just another statistic to know. You're responsible for knowing it, and when you get to college, you will see r squared show up in research studies. So something to know why we have it, know what it means, know how to calculate it, get between r and r squared. That part should be easy. And there you have it. So again, knock out set 2 after this video. And tomorrow, you will be able to watch the next video, which will further explore our scatter plots. So until then, have fun.